We learn the rules for perfect shapes early on. If you need the area of a rectangle, you multiply length by breadth. For a perfect circle, it's pi times the radius squared. But the physical world rarely builds in perfect squares and circles. Take a modern wash basin. It has straight edges that suddenly sweep into asymmetrical slopes. Our basic area formulas stop working here. The shape is irregular, defined by a collision of straight boundaries and sweeping curves that no single equation can describe. Standard formulas are designed for perfect geometric ideals, which means we need a different framework to measure the irregular spaces found in the physical world. It starts with a secant, an infinite line slicing a perfect circle at 2 points. Ignoring the lines outside, the finite section trapped inside is a chord. This chord traps a slice of space against the outer edge. This curved pocket is called a segment. The segment is exactly the kind of awkward, irregular shape that breaks our standard formulas. There is no single equation you can plug numbers into to find its area directly. To measure this, we have to reverse engineer the problem and carve out the answer from shapes we already know. If we draw 2 straight lines from the ends of our chord directly to the dead center of the circle, we enclose the segment inside a larger shape, a pie slice, known as a sector. Unlike the segment on its own, this entire sector is easily measurable. It is a rigid, proportional fraction of the full 360-degree circle. Once we determine the exact angle where those 2 lines meet at the center, we can calculate the area of the entire pie slice. By extending our view to the center of the circle, we have successfully trapped an unmeasurable shape inside a perfectly measurable system. But the sector isn't entirely made up of our target segment. The space sitting right above it forms a perfect triangle. To find the area of that triangle, we need its height. We drop a perpendicular line straight down from the center to cut the chord in half, creating 2 right-angle triangles. Basic trigonometric ratios, sine and cosine, allow us to translate the circle's radius and that central angle into exact measurements for the triangle's base and height. With those 2 lengths established, the total area of the triangle is unlocked. Now we execute the final step. We take the area of the entire sector and we completely subtract the area of the triangle. When the triangle is removed from the visual space, the only thing left behind is our target segment. The exact area of an irregular segment is always the sector minus the triangle, proving that subtraction is a tool for isolation. Let's apply this to a complex physical object, calculating the surface area of a round table featuring 6 intricate curved petal designs. Measuring 6 floating, curved shapes directly seems like an impossible, time-consuming task. But if we map the hidden geometry of the table, we find a perfect circle with a regular hexagon sitting in the center. The 6 petals are the spaces left between the hexagon's straight lines and the circle's curved edge. Complex physical problems almost always hide rigid geometric frameworks waiting to be decoded. First, we calculate the area of the full outer circle. Next, we calculate the area of the rigid inner hexagon. When we remove the hexagon's area from the total circle, we are left with exactly the combined area of the 6 petals. Finding the area of complex, real-world shapes doesn't require inventing a wildly complex new math. By mastering the relationships between lines, arcs, and angles, we can solve dimensional problems by simply carving away the shapes we no longer need.